Good morning, everyone. My webcam wasn't working today, so this video just got way better. Well, anyway, here we are with the Sn2 reaction, and I want to start off by reminding you we had covered Sn1 before this, and that was a reaction where we substituted the one group for another group on the molecule. So here we had a leaving group leave and a nucleophile come in, and there you go. So we're going to do substitution again today, but this is going to be a slightly different mechanism. So how it works and what kind of evidence there is for it is going to be different. So in this case, we have the same thing we did before, a molecule with a leaving group, usually an alkyl halide or an alcohol. And then we have a nucleophile, and it's going to react differently. Instead of the leaving group leaving first, we might have something that doesn't really like to form a carbocation. So in this case, or we might have a strong base that might have more of an effect on the rate limiting step. So let's start off with the mechanism. How this works is, I think, best demonstrated by an animation that I saw. This is from Gale Interactive. So what we have in this reaction is a hydrogen sulfide ion acting as our nucleophile, and it's going to attack carbon because of a slight dipole here from the bromide being more electronegative. So partially positive, partially negative. And this lone pair is going to attack here. There's an orbital here, a molecular orbital. And this will come in and attack. Let's slide the reaction time over. So as the reaction proceeds, notice the sulfide is coming in, and it's starting to make a bond with the carbon. Now at the same time that it does that, this bond starts to lengthen as well. Let's back up and see that. Do you guys see? As these two come together, that other bond starts to lengthen and starts breaking as well. And it's going to eventually break off. Now let's get to that middle point. That high energy transition state is right here. This is the maximum of the energy curve. And notice what happened to the hybridization of this carbon. It was tetrahedral, sp3, and now notice it's completely flat. So this flat sp2 is now pentavalent. 1, 2, 3, 4, 5 things sort of attached. 2 things are pseudo-attached here. This one's coming on and this one's going off. And right at this point, we see this bond starting to form and this bond starting to break. And notice here as well, the sulfur is bent shape because, like oxygen, it has 2 lone pairs. So now as we proceed, notice that the sulfur is going to become strongly bonded here. So this bond gets shorter and this bond is going to get longer and eventually break off. And what we have is the electrons actually go with the bromide ion to give it an octet. And we've got our carbon now with an octet as well. Now notice the stereochemistry of this reaction. Remember at the beginning we had this orientation, and this is achiral, but imagine if it was like 1, 2, 3, that would be R, let's say. Okay, so as we proceed, notice the nucleophile comes in from the other side, and that makes it 1, 2, 3. That makes it S now. See, so it's going to have a different orientation than over here. All right. But this is achiral, so you just have to watch out for the chirality. You do not get a racemic mixture in this case. You have the nucleophile come in on the opposite side of the leaving group, and that's for steric hindrance reasons, as well as the way that the orbitals, molecular orbitals are. So the mechanism can be shown simply on paper by the nucleophile coming in and attacking the partial positive carbon here, which is connected to the leaving group, and then the leaving group taking off, and this is happening at the same time. And then I have a typo here. The leaving group technically doesn't have a hydrogen on it, so it's going to leave with a negative charge. All right, so let's take a look down here. Basically, this is practice with the mechanism. Identify the nucleophile, so we can see the nucleophile is our Lewis base, and here's our electrophilic carbon right here. So we're going to show, here's my electrophile, and we're going to show the mechanism with the curvy arrows. So this comes in and attacks, and this leaves. So that gets me this molecule with a bromide leaving group. Okay, I'm drawing in all my lone pairs. I think it helps for you to identify. You see, the nucleophile is often very electron rich, so I think it helps a lot. All right, go ahead and practice doing that for each of these cases. Let's come back and check our answers. All right, guys, so we're back, and I wanted to point out a typo here. Did you guys see it? This iodide has to have another lone pair. There we go. So we're just doing substitution. Notice here's the leaving group. So we should circle it, and it leaves, and then it gets replaced by the nucleophile. In all of these cases, except the last one, we end up with negatively charged ions, and then here we have water. Notice all of these are pretty stable by themselves. So that helps to make the leaving group leave if it's more stable when it's separated from the molecule. All right, in this part, we want to consider the same reactions, but think about whether they're reactant favored or product favored. Okay, so here's how we do that. First, let's look at this one again. So remember, this one came in and this left. And keep in mind, this is very different from our Sn1 reaction, where the leaving group left first. Now, to consider which side pushes, does this push forward or does this push back? One thing that we need to consider is how strong a base this is. If this is a really strong base, it's going to be very reactive over here and push to the right. If this is a strong base, it's going to push to the left. So we want to consider the base strength between OH minus and Br minus. Whoever's the stronger base wins in pushing the reaction. So let's look at their conjugate acids. We know the stronger base has the weaker conjugate acid. So the conjugate acid of hydroxide is water, pKa of about 16, so 15.5. This one is HBr, and I just know HBr is one of my strong acids with a pKa close to 0. And that's all I need to know to get to the point that this is my stronger acid, so bromide is my weaker base. That means hydroxide is my stronger base. Now I want you to remember this term, strong goes to weak. So strong pushes to the weak side. So strong base is over here. It's going to react heavily and then turn these into products. More than this is going to come in and react here and push it back the other way. So in theory, this could be reversible, but in this case, with such a strong base, it's going to favor making products, and those products are too weak to go back. So this is going to be product favored. So please go ahead and rewrite these products again, practicing your Sn2 mechanism, and then do this analysis and figure out if we have product or reactant favored. And remember, reactant favored means no reaction. All right, guys, now we're back, and I'm showing the conjugate acid. That's very important, okay? It might be obvious when these are negative, but if they are neutral, it's sort of hard to remember. You got to add the hydrogen and look at the pKa, because in this context, this is the base, so you have to look at its conjugate acid, all right? So this is an alcohol. Its conjugate is an alcohol, so that's about 16 pKa. This one is HI, very strong acid. I just remember strong acids are about 0, and as long as these two numbers are very different, that's fine. So I'm going to go from very strong acid is a very weak conjugate base, and this is stronger, so we're going to go this way. So this is, again, product favored. And then in my last example, the HI is, again, about 0, and H3O plus is about 0. Remember, I have to look at the conjugate. Don't look at water's pKa. Water's acting as a base in this case. So its conjugate is H3O plus, which is also strong, about 0. And here, because I have two zeros, I have to say, well, maybe I should use my chart and find out who's slightly stronger. So HI is negative 5.2 on the chart, and H3O plus is negative 1.7. So HI is a stronger acid by, almost difference of pKa units of 3, so that's 10 to the 3 difference. Okay, so that's actually quite a difference. If these numbers were only different by, less than 2 pKa units, then we pretty much consider them reversible. You need about a difference of 2 or greater to say, oh, that's more than 100 to 1. So in this case, it's about 1,000 to 1. So here we have the stronger acid. So this is the weaker base. This is the stronger base, but just, not super stronger, right? So here we have, not a great difference like we did up here, 16 versus 0, but it's still enough to say it's going to be stronger on the right, stronger base, and it's going to push slightly that way. So this is going to be reactant favored. Again, pKa difference of about 3 units equates to 10 to the 3. So there's about 1,000 more of these than there are of these because we're pushing this way. Okay? All right. So let's get to our reaction coordinate diagram. You saw in the animation that this iodine was approaching and this was breaking. So in our transition state, how we draw that is draw the iodine making a bond to the carbon in the center. Then that carbon in the center starts to rehybridize. As this iodine approaches, these groups repel that iodide. So they start moving this way. So here's my ethyl group, here's my methyl group, and here's my hydrogen. And that chloride bond with the carbon starts to get longer because that's getting ready to break off. All right, and sometimes you see this, the iodine becomes partially negative. It was fully negative, and now it's sharing electron density with this carbon. This chloride was sharing electron density, and it's doing the opposite. It's going to take on more negative charge as it leaves. And this whole thing is a transition state. This is my Teen Wolf, remember? So this one is undergoing transition, and it doesn't stop there. It's just what's happening right there at this maximum point. So mechanism-wise, let me show that in a different color. We're showing the iodine lone pairs coming in and attacking, and this chloride leaving with the lone pair. Now, how many steps are in this reaction? Okay, so 1. Okay, 1 step with 1 transition state. There's no intermediate. This is a transition state. It's different from an intermediate. And usually in the transition state, we're showing the bonds breaking and forming, whereas an intermediate is sort of like a product in the sense that it gets formed from a step, but then it goes ahead and gets used again in a subsequent step. Now let's also look at the stereochemistry here. Is this molecule chiral or achiral? So it turns out this molecule is chiral. It's got 4 different substituents on it. Okay, so if we try to figure out R versus S for this, let's look at it again over here. So figure out R or S for this molecule and R or S for this molecule. Go ahead and figure that out. So over here, chloride is 1, ethyl is 2, methyl is 3, hydrogen's in the back, so that's 4. 1, 2, 3, so that's counterclockwise with number 4 in the back. So this is an S configuration. Over here I have 1, 2, 3, and 4 in the back again, and this is going to be R configuration. So you can see one feature of Sn2 is that if we start with something chiral, we get inversion. R molecules turn into S and S turn into R. The last thing about this is the rate order. Notice for Sn2 that the 2 is referring to what we call bimolecular. It takes 2 molecules that affect the rate. Okay, so it's both reactants. In our case, we have the nucleophile as well as the molecule containing the electrophilic center. So I'm just going to call that the electrophile. So the rate depends on both of these because remember, this is coming in at the same time that this is leaving. So they're both involved. So for Sn2, notice that if you double the nucleophile, that's going to double the rate. And if you double the electrophile, that should double the rate also. So when you have both of them doubled, that will quadruple the rate. Okay? So nucleophile times 2, electrophile times 2, concentrations. That means you have an effect of quadrupling the rate. All right, so the apparent order of this reaction is second order, which is called bimolecular. Putting it all together then, we have Sn2 reactions. They're substitution reactions. They involve 1 step, and the nucleophile attacks the carbon electrophile. that results in displacement of a leaving group. This reaction is same side or opposite side collision. Well, the nucleophile comes in opposite side of the chloride leaving, so this is called opposite side or backside collision. That results in inversion of stereochemistry. We saw R turning into S turning into R. That's considered inversion of stereochemistry. And this reaction is bimolecular in terms of kinetics. So let's finish off with sort of Sn2 refers to N being nucleophilic, S being substitution, and 2 being the reaction order. So as homework then, figure out what are the differences between Sn1 and Sn2 with respect to their kinetics or rate law, with their respect to stereochemistry. What kind of products do you see? Do you see if something is chiral to begin with, does it give inversion or does it give racemic mixtures? Think about the mechanism, think about the energy diagrams. Okay, so these are all things that you should be looking at and comparing and contrasting Sn1 and Sn2. Now we're going to see that it's not so straightforward and things can go either Sn1, Sn2, both, or neither, and that's going to be the basis for our next video.